Okay, great. Thank you, Bayan, for your introduction. And also, I would like to thank the organizers for having me here. It's a great honor and a great pleasure to have this opportunity to present our recent work. So my name is Junjie Zhang from Shandong University, and here are some reference. If you would like to more details, you may refer to these papers. So here's an outline of my talk. First, I would like to briefly introduce the nickelate superconductivity and some my motivation. And then second, I would like to introduce a new crystal growth method that we proposed and we realized the ambient pressure flux growth for this rhodolensed purple and hybrid rhodolensed purple nucleus, single crystals. And then third, I would like to introduce our results on the superconductivity on this nucleus, TC at 92 Kelvin on high pressure, and then we then further push to 96 Kelvin. And then summary and acknowledgements. So first, I would like to briefly introduce some long history of this nickelate superconductivity. So actually, for the in the periodical table, the nickel is a neighbor of copper, and nickel oxides has been long explored for superconductivity. It can date back to 1983. At that time, Benoist and Mueller explored this perovskite nucleus for superconductivity. Of course, they did not succeed. And then after the discovery of superconductivity in cuprates in 1986, people started to work on this 214 phase of nucleus. And there are some reports on this possible superconductivity in the 214. However, no one else can reproduce this result, and it's not verified, so it still remains a mystery. And then in the 1990s, people start to work on these low valence nucleate materials. So initially by these phosphorate phases synthesized by Lacroix. And then in 1999, Anisimov and his collaborators, they predicted superconductivity in the square plane nucleus by doping. Then we started to work on this nucleus from around 2014 when I was a postdoc in John Mitchell's group at Argonne National Laboratory. We try to explore superconductivity at ambient pressure, and then we also grow a lot of bulk single crystals, including the perovskite 113, the trilayer, and they reduce the phosphorate samples, single crystals. We try to understand the metal-metal transition, the metal-insulated transition, and the possibility of superconductivity in this multi-layer nucleus. We actually found the origin of the metal-metal transition in these trilayer phosphoretangs as intertwined charge and spin density waves, and in the lithium nickel phosphorate, we saw charge and spin straps. And also, we discovered a new compound that's the precision phosphorate, showing some key features found in the cuprates, like the quasi two-dimensional structure, the low spin states, the large orbital polarization, and metallic state. This is a very close analog of the overdoped cuprates. And we propose that if we can dope electrons in this compound, we might be able to find superconductivity. And then we published that in 2017. And 2 years later, we all know the story after that. So the discovery of superconductivity by Danfoni and his collaborators at Stanford initiated the nickel age of superconductivity. And then 4 years later, the observation of signature of superconductivity around 80 Kelvin actually attracts more attention, worldwide attention on these nucleate superconductors. So after several years of intense research, there are two classes of materials show superconductivity. So first one is the square planar nucleus. However, this class of material only shows superconductivity in thin films at ambient pressure. The highest TC is around 40 Kelvin, reported by Arando. As we heard yesterday, the Julia Montes group, they also grow a series of multi-layer nucleus from four layer to eight layers, also show superconductivity. And the second class of nucleus superconductor is the octahedral environments. It show bulk superconductivity on the high pressure and show superconductivity at the ambient pressure in thin films. Among all the known nucleates, the highest DC of these compounds is around 80 Kelvin and remains for more than 2 years. So how to increase the TC of nucleus remains a central challenge. So actually, in my group at Shandong University, we propose to increase TC of nuclear superconductors by introducing chemical pressure. So specifically, we propose to explore superconductivity in the rare substituted 3 to 7 phases, because as we already know that in the nucleus, the trilayer nucleus show lower superconductivity transition temperature than the bilayer samples. So chemical pressure has been utilized to tune electronic structures. As I already mentioned in the trilayer phosphorate phases, when we substitute the lanthanum with praseodymium, we can tune the electronic structure from insulating ground state to metallic state. And then also in the ion-based superconductors, the chemical pressure has been utilized to increase around by 30 Kelvin from lanthanum to samarium case. However, for this bilayer nucleus, there are some theoretical calculations predict different trends. For the Tennessee group, they predict that lanthanum case is the best one. However, for the Westlake University group, they predict that samarium case may be double the TC on high pressure. So which one is correct? And we need to experiment to test this series. So experimentally, there's only lanthanum 3 to 7 pure phase has been reported. No other rare elements 3 to 7 compounds has been synthesized. So how to grow single crystals of this rare doped 3 to 7 case? So conventionally, the high pressure floating zone technique was used to grow bulk single crystals. And it started 12 years ago when I was a postdoc at Argonne. So we actually was the first to grow bulk single crystals using this technique. And then we also plot a phase diagram for the lanthanum case as a function of pressure. So for the case of materials I just mentioned, we proposed to grow in this rare doped 3 to 7. However, this high pressure floating zone technique is not ideal. As we can see that for smaller rare earth elements, we need to increase the partial oxygen pressure to stabilize the phase. So as I show here for the perovskite phase and the trilayer phase, the pressure increases significantly. So for the doped 3 to 7 phase, we also need to increase pressure. However, according to this phase formation diagram, we need to, when we increase the oxygen pressure, we would go into the regime of this phosphate 10 phase, and then we definitely will have some impurity phase like phosphate 10s. So we need to find some alternative method to grow these single crystals. Even for the bilayer pure 3 to 7 phase, high pressure floating zone growth is not perfect. As we already noticed, there are some issues in the 3 to 7 single crystal grown using high pressure floating zone furnace. The first one is composition in homogeneity. There are several reports on these single crystals. Some parts of them show superconductivity. However, the other parts, even from a small single crystal, show insulating behavior. And the second issue is the competing phases. So in the very narrow range, around 10 to 15 bar oxygen, there is a competing phase that's called the 1313 phase, which coexists with this 222 phase, as we already heard this a lot from the previous speakers. So it's very difficult to obtain a pure 2222 phase or the 1313 phase. The third issue is the intergrowth problem. The intergrowth is a common issue for the series of radiolation phases. However, for this work led by Professor Chen Jingwang, they actually doped praseodymium in the lanthanum 3 to 7 case, and then they can significantly inhibit intergrowth issue and obtain the bulk superconductivity. So motivated by these two, so first we want to make a reverse doped 327 to increase TC, and also we want to improve the crystal quality of 327 single crystals. And so we explored a lot to find a new method to grow single crystals. So we focus on the ambient pressure flux method. After long time exploration, we actually found the right suitable flux, potassium carbonate as a flux to grow these nickelate. So initially, we grow the tri-layer lanthanum phosphate, and then the bilayer, and we also designed a new hybrid RP phase, that's the 1212 phase. And that's around 2 or 3 years ago. So we already succeeded growing these single crystals. For the 1212 phase, actually, we designed this material and realized the single crystals for the first time. So the idea was simple. We want to keep the basic structure unit from the 327. That's the response that is responsible for superconductivity. And then we also want to introduce some spin fluctuations. So we introduce a single layer and stack them alternatively around C-axis. We use our new flux system to grow the single crystals, and we confirm the structure using X-ray single crystal diffraction and also as scanning transmission electronic microscopy, and we found both the average structure and local structure shows the perfect single layer and bilayer alternating structure. Initially, we did not observe superconductivity on high pressure, and last year, Professor Xianhui Chen's group, they observed superconductivity in this hybrid phase. The TC is up to 64 Kelvin. And more recently, we also observed superconductivity in our grow single crystals. So the discovery of this 1212 phase combined with the 1313 phase, they actually represent the first two numbers of a new family of hybrid rather less than purple phase for superconductivity. And we also heard previously that Zhou Chen's group, they have already synthesized the same film of this 1212, 1313, also the 2323. Although the 2323 we have never succeeded obtain bulk phase. Okay, so also for the tri-layer phosphate crystals grown at ambient pressure, we also observe superconductivity up to around 29 Kelvin TC on set under high pressure, which is consistent with the high pressure floating zone grown crystals by Professor Zhou Jun's group. So back to this 2222 phase, we actually have single crystal diffraction, and STM results show very nice crystal quality. But when we use the nuclear quadrupole resonance to check if we have any intergrowth issues in these as-grown single crystals, we found the sharp peaks around 16 megahertz. That indicates the existence of short-range intergrowth, which is not good for superconductivity. The good news is that in our crystal growth, we do not see any competition between the 1313 and the 2222 phase. So to grow then we moved to grow the reverse doped 327 phases. So we can grow single crystals as large as 220 micrometers on edge. This is a SEM image for the semanium case. So we characterize our single crystals from the average structure. We checked the composition across the single crystal around 118 micrometers. We can see that the composition is very homogeneous, and from single crystal diffraction, we can see nice high quality crystallinity, and from the nuclear quadrupole resonance, of course we see a broad peak, but this is quite similar to the presidium case, which shows significantly reduced intergrowth. And also we use STM to check the local structure. We found that in tens of nanometers, we see perfect stacking of this bilayer structure. Before we proceed to measure the physical properties, in particular resistivity under high pressure, we want to make sure our oxygen content is close to stoichiometric 7. So we anneal our single crystals for a long time, and then we measure the oxygen content using TGA method. We can see that the oxygen content is very close to 7. And then we have obtained the right phase, the right high quality single crystals, and the stoichiometric oxygen content. So we measured our single crystals under high pressure because at ambient pressure, it's definitely not superconducting. So the single crystal shows zero resistance at 73 Kelvin, which is the highest among all the known superconductors, nickelate superconductors. And the TC onset is around 92 Kelvin. So we first push this nickelate superconductivity to 90 Kelvin range. And then we also observe the messenger effect in the direct current and magnetic susceptibility measurement. But the TC is around 60 Kelvin, a little bit lower than the zero resistance temperature. So we also want to know the structure, crystal structure at under high pressure. So we measured these polarized single crystals, use synchrotron X-ray powder diffraction at the room temperature. We can see that from these diffraction patterns, with the increasing of pressure, we can see the structure changes from monoclinic to tetragonal phase at around 18 GPa. However, with the decreasing of temperature, the structure may change. So we want to check the crystal structure on the high pressure at the low temperatures in the superconducting state. We can see clearly also the structure changes to tetragonal phase at the low temperature and high pressure. We can see that at 64 Kelvin, around 18 GPa, we still have the monoclinic phase, but it's already in the superconducting state. So our results show that for this compound, both monoclinic and the tetragonal phase can support superconductivity. So we summarize here by summarizing all the transport data and the structure data in this phase diagram. So the x-axis is pressure, the y-axis is temperature. We can see three regions, three phases in this phase diagram: the superconductivity and linear in temperature resistance. That's a signature of strange metal behavior, and this lower pressure metallic behavior. And also we can see that for this in this phase diagram, both monoclinic and tetragonal structure can support superconductivity. I want to mention that at the lower pressure, we actually do not see signature of metal-metal transition like observed in the pure 327 phase, and that was attributed to formation of density waves. So since we can now observe superconductivity up to 92 Kelvin, then one natural question is, can we push the TC to a higher temperature? So to realize this, we actually analyzed the crystal structure at ambient pressure, and we found that there's a correlation between the TC on the high pressure and the ambient pressure in plane distortion, as we define the delta as A minus B divided by A plus B. We find that with the increasing of the in-plane distortion data, the TC maxima increase also increases. So guided by this insight, we want to increase data more, and then we can increase the TC of nucleus on high pressure. So we grew a lot of other compositions, use the flux method and ambient pressure. And then we extracted the lattice parameters by Rydberg refinement on polar diffraction patterns. Here, just plot the in-plane distortion data as a function of rare elements. We can see there's a dome shape for this data. The largest data is from neodymium case with neodymium equals to 2.113 from EDS measurement. And the second largest number is from samarium around 1.43. As I already mentioned that the TC is correlated with this data. So we want to measure these two samples under high pressure to check if their TC is higher than what you have obtained. So for currently, the neodymium case for the neodymium case, the single crystal is very small. It's around maybe 20 micrometers, so it's not suitable for high pressure measurement. Fortunately, we have obtained around 100 micrometer single crystals for this samarium 1.43 case, and then we did high pressure measurements use helium as the pressure transmitting medium. We see clearly the superconducting transition around 96 Kelvin, and also shows very suppression effects by magnetic field. This validates our strategy to increase the superconductivity transition temperature among these nucleates. Okay, to summarize, we actually propose a new crystal growth method to grow high quality single crystals of radiolensed and hybrid radiolensed purple phases. And for this method, we do not need any high pressure oxygen pressure, and it is very easy to access. And we already obtained around 200 micrometer single crystals. And the other side, we have increased the TC of nickelate superconductors from 80 Kelvin to 96 Kelvin. And we also provide an effective strategy to further enhance TC. Maybe it's probably to 100 K, something like that. Currently, we are still working on this neodymium case. Okay, finally, I would like to acknowledge all my collaborators. So in my lab, all the work was done by my PhD student, Fei Li. And for the high pressure resistivity measurement, we collaborated with Professor Zheng Shi and Dr. Peng Di from HP Star. And for high pressure magnetic susceptibility, Professor Zheng Shi and Dr. Peng Di did the measurement. For real space imaging, we actually collaborated with Professor Zheng Qiang from National Center for Nanoscience and Technology, Chinese Academy of Sciences. We collaborated with Professor Zhou Rui for the nuclear quadruple resonance spectroscopy to check the intergrowth issue. And for single crystal diffraction, we collaborate with Professor Yusheng Chen and Dr. Tie Yan from University of Chicago and Professor Geng Huyang from HP Star for high pressure single crystal diffraction. For the synchrotron X-ray plot diffraction, we collaborated with Professor Zheng Zhang, Professor Deng Jiaoshi, and Dr. Peng Di from HP Star. And for the theoretical work on this hybrid 1-to-1-2 phase, we collaborated with Professor Guangming Zhang from Tsinghua University. Now he's faculty at Shanghai Tech University. That's all on my talk. I will stop here, and I'm happy to take questions. Thank you very much.
Thank you, Professor Zhang's nice talk. Any questions from the audience? Okay, maybe I can lead a question. I always had a naive question for the bulk synthesis. Oh, actually, Mike Norman, Professor Norman, please go ahead.
Hi,
So
Mike.
Junjie, how you doing? Nice
Good. How are
flying
you?
Lucy. Recently Haihu has been able to make 4310 single
Samarium?
with samarium.
Yes.
So have you guys thought about trying to do a pure samarium 327?
Samarium 327, we tried, but for our method, we cannot achieve pure 327 for the samarium case.
Thanks.
Yeah. Probably we have the solution limit for these compounds.
Professor Zhou Hua, please go ahead.
Junjie, yeah,
Hi.
yeah, Junjie, it's very nice talk. So, a quick technical question. So, because you mentioned your scrolled single crystal also not, perfect stoichiometry, you also have some delta, and then you do some annealing using
Yes.
high pressure oxygen, right?
No, we use very low pressure.
A low pressure.
We use 1.5 bar oxygen.
Oh, okay.
Yeah.
1.5 bar the oxygen. Okay, so not very high pressure. Okay. So
Yeah.
so for single crystal, you don't really need ozone to do the annealing like thin film, right? Or ozone, that does not, help much. Because I remember for thin film looked like only ozone work, right? Because using pure oxygen, it looked like thin film annealing does not really, help much to realize the superconductivity. I mean, from
Yeah,
a raw sample. Yeah.
yeah, one nice question. So we actually tried ozone, but we found some other bases.
Oh,
So
okay. Some new
okay,
faces. Okay.
yeah, yeah. So we tried ozone for this 3 to 7, but we were working on this on the 3 to 7 powders. Um, so we can see as synthesized the samples is 3 to 7, but after use ozone we obtain a new phase. Uh, this phase actually shows do not show superconductivity, but any signature of superconductivity for this new phase. So in our case, we think the ozone annealing is too strong oxidizing for the bilayer phase. But
Okay.
for the cement case, actually, we have some new work on this, and we can see this phase become still also rhombic phase, but the oxygen content goes up to 7.3. For these 7.3 samples, no superconductivity was observed, uh, both at ambient pressure and high pressure. We measured up to 30 GPa. It's still metallic.
Okay. Okay, great. Great. Thank
Yeah,
you.
thank you.
Question from Zhang Yu. Go
Oh,
ahead.
hi. Hi, Professor John.
Hey,
Thank you for your
hi.
very nice talk. So I have two questions. So the first question is for the samarium doped lanthanum nickelate 327.
Yes.
So when I first read your paper, I noticed the ratio for lanthanum versus samarium happened to be 2 versus 1. Do you think that's a coincidence, or is that because like samarium and lanthanum they forms some kind of order, like so that they have a integer number ratio?
We can control this.
Okay.
So
Mm,
it depends on how much what's the raw ratio for the materials we put in the crystal growth. So when
okay.
we use this 2 to 1 ratio, so we
Mm-hmm.
obtain nearly 2 to 1 for the single crystals. When we increase this amount, so for example, we use 1 to 2 ratio for the lanthanum and rare ratio. So we can grow as high as 1.43. But this one, of
Okay.
course, is did not reach 2, right? So
Mm-hmm.
that's a solution limit here, as I just replied to Mike's question. So
Okay.
there is a solution limit, but we can kind of control the ratio for these lanthanum and rares.
Okay. So you believe the on the rare earth side, these lanthanum and the samarium they are disordered. They are not forming any ordered structure. So you can basically.
Yes, they are disordered, but
Mhm.
from our single crystal refinement, they are
Mhm.
not completely random
Mm.
distribution. For the length side, we have two sides. One is between these bilayers, right? And the other one is within this bilayer. So
Mhm.
we found that the samarium occupies mostly the length side between bilayers. For the inner one, it occupies a smaller portion. And this
Mm.
also verified by the STM results. We actually checked those from the EDS map. Let me show you here. Yeah, so we can see clearly
Okay.
here from the Samarium case,
Mhm.
mostly occupies the side between the two nickels, between the
Okay.
bilayers, right?
Okay. Thank you. And I have a second question. So you mentioned that you have tried potassium carbonate as a flux as well as many other flux. So do you have any like general comments on what might be a good flux for this nickelate system? Because the other Professor Xianhui Chen's group they use a mixture of sodium chloride and potassium chloride. Also works for the lanthanum nickelate. So do you think, in your opinion, what's the important aspect to consider when you are choosing the flux to do the nickelate synthesis?
Yeah, actually, that's a very nice question. So for the actually, as far as I know, there's no reliable theoretical prediction
Mm,
which flux can work for a specific material. So basically, it relies on experience and exploration. So actually, we try to we explore the different flux systems
mhm,
for a long time, and we tried. Of course, we first tried the most common used flag
mhm,
systems, like like these candidates.
mhm,
But for some of them, we do not see any faces. For some of them, we see some perovskite phase. But when we check these, use a microscope to see if there are any shiny faces, we do not see any. And then we found some literature for crystal growth of the rare rhodium oxides, which
mhm.
is also a transition metal oxides. And then we immediately try to grow this nucleus on this sample for this flux system, and we succeed. As also you mentioned that there are some other flux system works for the nucleate single crystals. As you mentioned, Professor Xianhui Chen's group, they use the sodium, potassium, right?
Yeah,
Chloride.
chloride,
Yes.
yes.
And they also a team from Korea. They also use cesium chloride.
Mhm.
And yeah, so basically, I think it's just based on experience to explore. Actually, for our exploration, it takes around 3 years before we
Okay,
find
okay.
the right one. Yeah,
Thank you so much.
thank you.
Okay. Any last minute questions? We're 2 minutes over time already.
Hello,
Okay.
Junjie. Can I ask a question?
Oh, hi.
Hi, very nice talk. I think you can keep increasing the ratio of samamio atoms compared to the lanthanum. Means, for example, as you mentioned, more samamium atoms goes to the positions between bilayers. So if you keep increasing samamium atoms, probably
Mhm.
you can get higher TC. Are you trying to do that?
Thank you, Professor Yao. We actually tried a series of compositions, and from our current growth conditions, the limit of semaglutide is around 1.43. That's from EDS measurement. Of course, they have some air bars there, but it's pretty close to 1.5. And for the
Okay.
others, so we hope to increase the amount of selenium, but for the current method, it seems that's the limitation. We can consider some other techniques to increase. If possible, if we can obtain the pure 327, they might have much higher superconductivity transition temperature.
Okay,
Yeah,
you
and
can
also
try.
we heard from Professor Wang Meng's work. They also show an increase of superconductivity transition temperature from the samarium case and also the neodymium case. But their polycrystal powders seem they can achieve a higher doping level. For our single crystals, it seems 2.11 something is the limit. Yeah.
Okay, yeah.
Yeah, we have tried to increase more,
Yeah,
but seems it's very difficult.
okay, there is probably optimal doping for different rare earth compounds. Okay, you can
Yeah,
try.
but we are limited by current
Okay.
growth method, right? So if there are some new methods, then we probably can achieve more.
Okay, very good. Thank you.
Thank you.
Okay, maybe we can wrap up the discussion.